So last time we stopped on LU. How far exactly did we get? We talked a little bit about, I think, just the formulation of, I think, of LU and started talking about algorithms. Never got to anything cost analysis-wise. So first, maybe I should actually just kind of remind people, remind everybody how LU looks like and how we can derive basic algorithms. L and U such that they represent A exactly, where L is lower triangular and U is upper triangular. It helps to write this out to derive any kind of algorithm in blockwise form. And so when we get a form like this, we get several equations, right? So the blocks I did right here are 0. And so we must find L and U to satisfy this, where these diagonal blocks are themselves also respectively unit lower triangular and upper triangular. So to do so, we have immediately some equations we can observe that, for instance, A11 is L11, U11. Which means that we can compute this factorization of A11 independently of anything else. So that will be our first step. Then we can figure out, based on these equations, that A21 is given by, these guys times these guys. So L21, U11. So what we need to do to figure out L21 after we have solved for L11 and U11.
U11 inverse times A21.
Yeah, so we need to solve a few systems of linear equations, and we can do so by solving we don't necessarily want to invert U11, but we can solve this equation for L21. We get a similar equation for A12. That would be these guys times these guys, so L11, U12. And so what, then I guess we do something that's very, very similar. We solve with respect to U12. So now we've gotten L11, U11 directly from A11, L21 from A21, and U11, U12 we've gotten from A12 and L11. It remains only to find L22, U22, and those we can derive based on the equation for A22, which is so how would we compute? So here, this is known as this. So what are we left with to do to compute the rest of the factorization, namely L22, U22?
Find the LU factorization A22 minus L21, U12.
Right. So we want to factorize A22 minus L21, U12, which will give us L22, U22. So this is the Schur complement. I usually say Schur complement update. So yeah, this is the general form of, in fact, a lot of different LU algorithms. So the standard method that you have most likely seen first we just start out with L11 being a scalar and U11 being a scalar. And then we can think of these as vector equations, where we are solving for a single vector L21 and U12 at a time. Then we're doing a vector outer product update to compute the short complement update. And then we're moving on to the next entry and factorizing and computing the next diagonal entry in U. So L11 in that case would just actually be the entry 1, so this unit of the triangular. This is going to be most useful in the context of the algorithms we're discussing when we think of L11 as a small block. People think of A11 as a small block. L11 has dimensions. This is A21. A12. So we'll often have that we want to factorize a panel, a tall and skinny matrix, or update a panel, and our trailing matrix updates will in general be a few different vector outer products. So these are just. However, there is yet another algorithm one can derive from looking at the problem in this way, which is to say that partition is evenly and recurs. So compute the rest of this operation recursively. Then at every recursive step, what we have to do are triangular solves and matrix multiplications, and these two recursive calls. So this is also. So there is also a recursive structure here that is common to many algorithms. In particular, it's quite important that this recursive call is dependent on this recursive call. If you look at the recursive structure of matrix multiplication, you do not have that dependence. Okay, so that's kind of just abstractly what we can get out of thinking about different ways of partitioning our original matrices to derive different LU algorithms. Yes, Carl?
How do you find out L11 and U11?
So you would do recursively an LU factorization of A11.
Okay.
So if A11 was just a scalar, then you would say U11 equals A11.
And second 1, 1, 2, 1?
And U12 is actually also A12. Then A21 would be, L21 would be A21 divided by U11. So U11 is kind of the non-trivial entry. And if we're doing kind of a recursive approach that continues with this, it would eventually get to a base case that's diagonal. And at that diagonal base case, we know how to handle things. It's again the same way. We set U11 to be the entry of A, and we set L11 to be 1. What's often this U12 is not mentioned at all, because if you look at the vector version of this, U12 will just be A12. But if you want to design a block version of this, that's not the case, and we have non-trivial triangular solves to do here. The only reason U12 would be equal to A12 is if L11 is the identity, which is never is, except in the case when its dimension is equal to 1. So it's just a scalar equal to 1. Okay. So, any other questions about this? This is a little bit separate from the slides, but I thought I would just kind of cover this because this is how I think of LU factorization. Another way of thinking of LU factorization is of kind of successive eliminations. And thinking of Gaussian elimination as introducing zeros into the matrix. That's also a good way to think about it that will arise, that we'll talk about a little bit when we talk about pivoting. But in general, this type of partitioning strategy where we can use a block form of the matrices to pick either a recursive strategy by picking these dimensions to be the same, or some kind of block strategy are very common to matrix factorization algorithms and different algorithms that have to iterate through the matrix. So you can write similar things for QR factorization and SVG and other triangular solve-like problems, and you will get different things reflecting the differences in these problems. So the dependencies look somewhat different. Of course, you can also do this for matrix multiplication, and you would find that there are 8 equations corresponding to 8 recursive calls you can do, and that allows you to write a recursive matrix multiplication algorithm. The recursive algorithms actually are interesting in their own right if you look at their parallel complexity, they are usually not worse, although there are kind of complex trade-offs. In the slides for this course, we are going to be mostly working with what I would call iterative algorithms in the sense that they, rather than recursively partitioning the problem, kind of compute panels and then move on, or compute blocks and then move on. In other words, blocked algorithms. But kind of an alternative way to view a lot of these things does exist. One of the reasons to view things in a blocked way over a recursive way is that we often deal more precisely with the data distribution. So if we want to control the data layout, when we say recursively compute L11 times U11, we need to say a little bit more if we want to see how that's done in parallel in terms of how are those matrices laid out, what are our assumptions as we recurse on the layouts of the matrices. But actually all of that's possible as well. Okay, so with that detour, let's go back to the slide we had started last time on LU factorization and how to do it in parallel. So usually we want to do LU to solve a linear system, although that is not the only method we could use to solve a linear system. And one should really think of this as the problem, and LU is one particular algorithm of solving it. So as we'll see, there can be other algorithms that make more sense when you want to do it in parallel. So the way we usually solve this is by factorizing A into these L and U, then solving for UX all at once by writing that as Y, and solving this triangular linear system, which is dense, and then doing the upper triangular system solve, which is essentially the same thing as forward substitution followed by backward substitution. Do you think these are as easy to do as matrix vector multiplication when we think about them in parallel? Once we have the LU factorization, we have the L in the matrices. What we have left looks like a couple of triangular system solves. They're going to be a bit harder than matrix vector multiplications. Yeah. They're doing triangular solve is more involved, and I think that will actually be what we cover in the next set of slides. So I'm actually going to do that out of the order that Mike had it, because I think this is more natural. But first, let's study how we actually compute the LU factorization. But it is worth keeping in mind that once you have it, these steps are non-trivial to solve in parallel. In particular, as we do substitution of equations and solving them, we need to solve for some variables before others. So we have a critical path and a depth that is generally n. So the algorithm is not very parallel in a sense. But we'll come back to that. So now let's return to LU factorization, and let's remind ourselves of the different ways we can proceed while doing it. The form that matches kind of this blocked version and also is going to be vector form as well is this outer product formulation, where we compute a vector of L at a time. So we look and compute a new L entry for every A entry in a column. Then we perform this update. And this update is the same as saying Aij minus Lik times Ukj. Ukj is the same thing as Akj. Here we're just kind of rewriting things, and A has already become U for that row. Because once we've kind of reached a block size equals 1 here, when we do the solve, L11 is just a unit entry. So we do this outer product, which is exactly our sure complement update, except here written in loop form. Okay. So as we discussed, overall this cost n cubed over 3 multiplies and adds taken together. No, just one. Let me get this wrong again. But anyway, we can then study different loop orderings that can arise in LU, and so some of them will be outer product-like in the sense that they do these updates as soon as they compute the panels of L and U. The other ones will be, in a sense, more matrix vector-like. So they will say, once we've computed a part of L and a part of U, let's now look at the original A here, perform an update, and only then compute its factorization, and only then move on. So they essentially take a matrix and multiply it by this vector in order to update this part. So they are, in a sense, a dual to the outer product, as matrix vector multiplication is a dual to it. So in both cases, as if you remember, we have one matrix involved in two vectors. In one case, two vector operands and a matrix output. In the other case, a matrix input, a vector input, and a vector output. But one can use either of those as primitives, or kind of their blocked versions as primitives to implement LU factorization, and also other density algebra methods. Okay, so there's some trade-offs between these. In particular, you can look at whether they are good in terms of read and or write locality, but we discussed that last time. So we can save some amount of work when we do the outer product ordering. This is natural. And finally, if we now start trying to apply our design methodology for parallel algorithms to LU, one way we could do so is by associating a task with every matrix entry. So this is our fine-grained tasks. And for each of those, we potentially have to do a non-trivial amount of work, right? So if we associate each fine-grained task with doing all the updates for a given entry of A, how much work could it potentially do? And cubed overall, but n for each task, right? So for each entry of U and L, you can again, I always just think about everything geometrically from the cube. So we had a cube in matrix multiplication, and we still have a cube in any kind of dense matrix factorization. It should look something like this. And so if we kind of fix a point on A and we want to do all the updates from it, or if we think about that as some point on L or some point on U, the updates correspond to to everything in that fiber, of which there is n. Also, you can just tell that there's n squared tasks and n cubed work in LU. So there should be roughly theta n work per task. So these are, in a sense, persistent tasks. So they can receive some information, do an update, and continue. Actually, to me, that's a somewhat unnatural notion of tasks. I think often in literature, a task is a coherent thing in parallel computing that executes sequentially, then ends and expires. Here, we'll talk about both tasks that kind of are, in that sense, pieces of work that are contiguous, but also tasks that are persistent. To which you send some data, they do some work associated, usually with some data entries. So here, kind of the tasks are partitioning the data rather than partitioning the work is one way to think about it. Both are good, they're just representations. So once we partition the tasks, we can try to infer the communication pattern at this fine-grained level. In particular, we'll notice that essentially all of our entries for a given entry of L will depend on everything to their left this way, and everything that's north of the diagonal, that's upwards from the diagonal. So to compute this entry, we finish once we've updated everything from here and here, and then once we've divided by this entry. We have something similar for entries of U, where we need to compute updates like that, and we usually don't need to do the divide there. So we're just done. So the communication pattern then should be that each point here, each task, needs to talk to and communicate with all the tasks above him and all the tasks to the left. So those are the two projections. And we can think of those usually as broadcasts because and entries here are needed by all tasks throughout this row. And similarly, this subcolumn here is needed by all tasks in the rest of the column. Okay. So this is one depiction of that, where we need to move L to 1, for instance, to update all of the entries in this row. However, it's worth noting that we don't, for instance, need U23 to compute U24. So these tasks are not, in a sense, communicating. This task is communicating with that task, and this task is communicating with this task. This is essentially already assuming a mapping of the communication pattern onto a mesh, where we might want to forward L21 through this entire column. So this is one way to view the problem. Okay, so we can write that as follows. At every iteration for a task, we want to receive something from a broadcast that corresponds to entries of U or entries of A. So something coming from my vertical column of tasks, and something coming from my horizontal row of tasks that corresponds to an entry of L, and then we do an update. And this is really where the bulk of the work happens. So every task at every iteration should do on average one update to corresponding to the Schur complement. At some point it will run out of work, so I say on average, but usually it does one unit operation. So after we've done the Schur complement update, we can solve for the new elements of L and broadcast the elements of U as well as the elements of L after doing this division. Okay, so this is how the fine-grained algorithm can look like in terms of broadcast. So here, essentially, we have at some iteration k, we've done this much, and we have all of these tasks broadcast their entries vertically and horizontally. So any task here will receive one entry from here and one entry from here and perform an update. Then we will take this entry of A and broadcast it down for this column and compute the new column of entries of L, as well as take the new column of entries of A to be just the updated entries from the previous iteration, and then continue receiving and broadcasting. So as in pretty much all LU algorithms, the bulk of the concurrency is coming from what stuff in the algorithm? I have to tell you, but that made it a question. Where are all processors going to be doing work? Where are the most amount of tasks working?
Broadcasting.
In broadcasting, yes, especially there's a lot of tasks receiving data. But in terms of the work, the computational work, what part is most parallel?
NN,
Sorry?
computing UNN and LNN.
So the final part of that computation, I would actually say, is not all that concurrent. So when we do, for instance, this division to finalize the entry of L, we only have n divisions that we do at a given time here, right? So we will only divide the particular entries in the column of L. But we do have parallelism in the process of computing L and U that is more parallel than this, just kind of this degree of that.
The update entry point in the first
Yes, exactly. The update, so the very first outer loop here, what's called the Schur complement update, this part, where we do the matrix multiplication, where we do the matrix multiplication here, is the dominant part in cost. When you study the algorithm working on vectors, so this fine-grained version, then the number of divisions we have to do is n at every step, and the number of Schur complement updates we have to do is roughly n squared. So that's where we actually can have all n squared tasks be doing some non-trivial amount of work. And so the general goal with parallelizing algorithms like this, in particular for LU factorization, is to make sure that the Schur complement dominates and the parallelism is well exploited there, and the other parts that are more sequential do not become an overhead. And the same is true for a lot of other matrix-based algorithms where you have a trailing matrix update, in a sense, is the generalization of what's the Schur complement update is called, and you want to ensure that your trailing matrix update, which looks like matrix multiplication, multiplication and you know how to parallelize well, dominates the other components of the algorithm, which are typically things like panel factorization. Okay, so that's a little bit about you. Okay, so we can agglomerate this from the fine-grained task graph in a couple of different ways. So we can combine things into 2D blocks. We can combine things into columns, or we can combine things into rows. So if we combine things into blocks, we have a natural layout and we preserve a similar communication structure. Again, really, and nothing in this block is dependent on anything in this block, but it's dependent on pretty much everything in that block. Okay, and so we can also visualize this with a picture where we start with the matrix A, and so now this is the 2D aggregated kind of block-wise version of the LU factorization. So we start by factorizing a single k by k block of A here. Then we need to do triangular solves with this triangular matrix and each of these three blocks, and triangular solves with this triangular matrix and these three blocks to compute the panels of L and of U. Once we have those, we can broadcast them down to compute the short complement and continue on with this 3 by 3 grid of blocks and perform the rest of the LU factorization. Okay, and so this describes roughly that. So this is the coarse-grained 2D algorithm that iterates essentially through your local columns and your local rows of that particular task, of this aggregated larger task, performs the block LU factorization, then performs a broadcast, and then update for the corresponding rows and columns. Okay, so the 1D version of aggregation produces a different communication pattern where we have to now move, again, L to the rightward task. But what communication do we avoid in this particular 1D column-wise blocking? Yeah, the vertical broadcasts become free. So the vertical broadcasts become free, but the horizontal broadcasts don't. And in fact, they become substantially more expensive, right? So now we'll be broadcasting, in a sense, a lot more. In particular, the problem is that we have maybe the same amount of overall data ever being broadcast, but the processor, there's not concurrency in those broadcasts. So in the 2D algorithm, we had that different aggregated tasks or different processors would own different tasks in this column. So when we do this broadcast, we could have different tasks send out different pieces. And in fact, only tasks in the same rows would have to communicate. This is inherent to the fact that we've done a partitioning that is lower dimensional, right? And we have a surface area to Varlin ratio that will not be very good. So you can think of this as, again, partitioning a cube, so where now we've partitioned it only in one dimension. So this is going to be no better than the scalability of 1D algorithms for matrix multiplication. In fact, it will be somewhat worse because we have dependencies throughout the algorithm. So if we do the row-wise partitioning, then we avoid having to communicate the L factor entries, but we still have to communicate the U entries, and it's about as bad. Although one thing to point out is that in this particular layout, what is one advantage and what is one thing we can do here that we can't do in the row-wise layout? Pivoting, right? So if we wanted to do partial pivoting, then we could compute the maximum entry of A locally within each task, within each aggregated task, and figure out which rows we want to pivot, which is potentially very important because once we go to a layout like this or to a block layout, then if we want to start doing LU with partial pivoting, that is, we want to figure out the maximum the maximum entry in the leading column of the trailing matrix, we will have to communicate for every time that column is distributed, which is most of the time, or all of the time. So that will be a problem. Okay, so now we can, given the agglomeration, start considering mappings of the agglomerated tasks onto processors, which is kind of a step that you can essentially merge into agglomeration if you wish to. What we'll do is in particular consider starting with a blocked aggregation, with a 2D blocked aggregation, then doing a cyclic mapping of blocks to processors on a 2D grid. And what this will yield is a block cyclic mapping. And I'll show a picture of that in a second. And so we can do similar things in the 1D case where we could create aggregated tasks containing different columns and then assign them to processors in a cyclic manner. So in that case, if we do 1D column aggregation with a cyclic layout, it would mean that the ith processor owns all columns of index I, p plus I, 2p plus I, 3p plus I, etc. So the reason we may want to do this is because when we looked at the blocked algorithm, what we could have noticed, this is going the wrong way, is that we had a lot of load imbalance. So, well, not load imbalance, we had not enough concurrency. So here only a single processor was working if this is just a single task. Here only these processors did work, and here only these processors did work. So if we assign each task to a given processor in just a blockwise manner, these processors would never work concurrently with these processors. So there would be a substantial amount of overhead there. So for that reason, we'll want to introduce cyclicity, which will provide us a way to reduce this basic block size associated with each panel factorization. And to essentially ensure that even in a kind of small minor of the matrix, so we might look somewhere here, if the block size is sufficiently small, then a lot of processors will still own things in this region. So if we have a 5 by 5 grid of processors with a block size of corresponding to kind of this little dimension, we would still have all the processors own data here, and they will still be involved in true complement updates once we've solved for most of the problem. And so, but this kind of does complicate what we have to do in the process, and does mean that we have to do panel factorizations that are thinner in order to actually exploit the extra concurrency. Okay, so, and we'll see those in a second. So this in particular is a 1D column aggregation with a cyclic mapping, where we've taken columns and designed a little 3-processor decomposition, where every processor owns a column, for instance, 0, 3, 1, and 4, and 2, and 5. Except I should have shifted that, but I want to actually be consistent with what's written. Okay. So when we do these 1D agglomerations, I think I already discussed this, we need to do one broadcast, and we have either concurrency or no concurrency in the panel factorization. The algorithms look only simpler than what we have in the 2D case. Something very similar happens with 1D row aggregation. I'll just go through this. And I want to talk a little bit more about what it means and what a block cyclic layout looks like. So if we, in particular, have a 4x4 processor grid and select the block size to be n over 16, in other words, have a cyclicity factor, I like to call it a 4, so that there is a 4x4 grid of blocks owned by each processor. So for instance, processor 8 would own these 16 blocks. If in a cyclic layout, the blocks would be of size 1, and this matrix would be 16 by 16, while in the block cyclic layout, each cell here is a little block of the matrix. So an assignment like this ensures that if we've completed, for instance, half of the factorization, that this minor of the block is still distributed over all the processors, and in fact is distributed evenly. Actually, cyclicity also allows you to ensure nice load balance as you design recursive algorithms. So if you wanted to partition L and U and A into n over 2 by n over 2 blocks and do everything recursively, you can think of partitioning this layout and recursing into either this block or this block. And so long as the number of recursive levels is logarithmic in the simplicity factor, we maintain that the blocks are distributed over all processors, while at some point the blocks will become, as we partition a block like this, it will be distributed only over a subset of processors, all the way down to one processor. So this layout is also consistent with kind of recursive hierarchical partitionings. Okay, and so in a layout like this, LU factorization will look like as follows. So we factorize first just this little block. So this part is done sequentially by our processor 1, so the first processor. Then we perform triangular solves. And now this is a much thinner panel, so there's less work involved. So we've essentially shrunk the section of the algorithm that's not as parallel to be kind of as small as possible to remove its overhead to the extent we can. And when we do the short complement update now, we can notice that all processors have some work to do, maybe a slightly different amount, but roughly the same. And that will continue to be the case as we iterate. So there's still components of the algorithm that are not as concurrent, but we can notice that they are less significant as part of the overall cost, because their cost will scale with this block size B. Yeah. So that's a basic idea of kind of distribution layout that we'll often use in matrix algorithms. Any questions about simplicity or block cyclic layouts? So effectively, these algorithms give you a tuning parameter that is independent of your number of processors in Excel. So you have this block size that you can make small if you want more concurrency, but as you make the block size small, you do make the execution tasks more fine-grained, which has its overheads. In particular, what do you think is the overhead of having a smaller block size in a layout like this and operating kind of with that as your sequential unit of work?
More steps. I mean, you have to go all the way down the PR.
Yeah. So there's more steps as that points out. So and so, what does that mean in terms of the cost analysis? So what do we have to do for every one of the diagonal blocks? We have to do a broadcast, right, of that block. We have to factorize it and broadcast it. Now we can think about what we have to do for every one of the diagonal blocks in sequence, because we're only processing them one at a time, right? So we have to do one collective call, and the amount of data we send there will scale with the area of the block, and the amount of work we need to do the factorization will scale with the volume of the blocks. So if we take the area of the blocks, which is like b squared for b by b blocks, and multiply it by the number of blocks, which is like n divided by b, we get n times b. So the amount of data we send for the diagonal blocks actually goes down with b, because it's n times b. And the amount of flops certainly does. If you add up all the volumes for all of the diagonal blocks, they will be of size n times b squared, n over b times b cubed, which goes down with the square of b. So as we reduce the block size, what is the one term that doesn't go down in terms of this diagonal part of the algorithm? Yes, the number of broadcasts, so which is the latency cost. So the number of messages we have to send will become bigger. So essentially, for each of these little blocks, we have to do a collective communication call. So, and the number of those is n over b for a block size of size b. So if we want to decrease the block size, we have to proportionally, in general, increase our latency cost, send more messages in proportion to that. And often, in fact, and for this problem formally, there's a trade-off between the amount of flops and the bandwidth cost and the latency cost in some regimes. So it's a parameter that you can pick. Okay, cool. So some potential other performance enhancements. Yes, there's other tricks you can do. I think the one I want to talk about most is look ahead. Yeah, and maybe let me just draw what that looks like because it's sufficiently important. So look ahead basically corresponds to doing pipelining of panel factorizations within matrix within a matrix factorization algorithm. It's something you can do for LU, but also for pretty much any other matrix factorization algorithm. And the basic idea is that we'll want to try to overlap two different updates. So we want to do an update like this and an update like this. And so to do so, we will first send the update here and then begin this factorization and this factorization as soon as possible. And while these processors are performing the trailing matrix update corresponding to these blocks, maybe let's call them L1 and U1, and this L2 and U2. So here we do L1 times U1 and then L2 times U2 roughly. So we want to compute L2 and U2, the next two panels, while performing the trailing matrix update A minus L1 U1, where this is some portion of A. So essentially, we want to overlap this trailing matrix update with the next panel factorization. And the idea is that the Schur complement update is where we want to be spending all of our time. So let's just throw the panel factorization, which is not sufficiently concurrent, and do it on the side in overlap with the trailing matrix update. So on this part, we can have all of the processors working. On this part, we only need usually a small subset, so a column of them. And we can appropriately stagger the work so that all of this happens concurrently. So it's a way to effectively fully overlap the computation that's going on using pipeline. And in practice, this helps quite a bit. You can really see a factor of 2 performance improvements if you do this well. It doesn't help with the fact that you aren't really reducing the communication costs. So you could potentially maybe overlap more communication through this, but the total amount of data that every processor receives and sends and the amount of messages and the general critical path length is not really affected, at least not asymptotically. So you kind of get a very nice factor of 2, but not usually more. Okay. Any questions about how that works? So I think this is the next part. Oh, no, execution time, right. So let's actually now analyze a little bit about what's going on in these algorithms quantitatively. So we can notice that for the 1 agglomeration algorithm, when we compute a single panel at a time, so here we have to do work, I guess that is B that's introduced. So and we'll work with the general notion that every processor works on a panel, broadcasts it, and then moves on to a new panel. We don't necessarily need to have 4 processors. For instance, this could be assigned to P1, P2, P1, P2, so that different processors, for instance, this would be a cyclic a mapping of a blocked 1D agglomeration, or well, if this is one particular column, if this is many columns, then this is a block cyclic mapping of a 1D agglomeration. But they don't look all that much different. So if this is of size B, this panel factorization is done purely by a single processor, and it requires this much time for flops, and it requires a broadcast of size NB, which requires log P messages. So we have one of those for each of the panels. So the total number of panels is n divided by B. So we can take the amount of work we have to do for each panel and multiply that by n over B to get the computational cost. So, that makes sense. And so does this computational cost, this can be greater than n cubed over P, right? So B is any greater than P, then it dominates n cubed over P. Does that mean that the algorithm does more overall work than the usual sequential approach?
How can B be greater than P?
Well, we could set B to be n, and then we'd have a cyclic 1D aggregated layout, column aggregated layout. But actually, if B is, oh yeah, that makes sense. Yeah, so we don't want B to be large. So this thing is n squared B. So if B is less than n over P, we're not work dominated. So if B is equal to n, we just have a cyclic layout, and so the size of this is 1, like the number of columns here is 1, B equals 1, and we just, we are actually fairly balanced in the computational cost. But when this size of the panel becomes very large, then we become unhappy. So I guess in particular, it would be when B is greater than n over P, and I guess you can notice, well, actually no, B is greater than, just n over P. So in that case, you actually don't have the full matrix blocked among all the processors again. But the point I wanted to show is that it's not the problem that the algorithm is not work efficient. The problem is that the algorithm is not concurrent. So in fact, the overall number of operations is still n cubed over 3, or 2n cubed over 3, depending on how you count. However, it may not happen sufficiently concurrently if we make the part that is sequential too large.
What is the n cube term in the computation? How do you get the n cube by P term?
The n cubed by P would come if you count the cost for the updates, of which overall there's n cube computation and the updates are fairly balanced, so long as you're good about doing this broadcast altogether or pipeline broadcast. So those should add up to n cubed over P per processor. But you have some overhead terms in general that come from these sequential portions here, and it might be clearer in the 2D case. So the overall execution time is then given by doing n over B broadcasts of size nb. So that gives us those two terms, n over B times, for the number of panels, plus this computational cost scaled by the computational rate gamma. So really all we care about is understanding the cost of the collectives, and then we can derive the cost expression for the algorithm. If we wanted to use a more precise model, that map, for instance, to a network topology, we could substitute a new cost for a collective here. So if we have a 2D mesh, a collective costs something slightly different. But for a kind of general connected network or a hypercube, what we get looks like a logarithmic factor. And so in general, what we want to do in this case is pick B to B theta n over P. Although we may be upset about the fact that the synchronization cost is relatively high. So we have something proportional to P there. Okay. So that's the 1D algorithm analysis. Any questions about how we got this execution time? Okay. So now we can study the execution time for 2D agglomeration, where we now perform the algorithm that we really spend more time talking about, where we have a B by B block. We perform factorization here, we broadcast this here, we broadcast that there. We do these factorizations, then we take whatever partitioning we have over here, do these broadcasts, and then perform these updates. Is the size of this broadcast always the same as the size of these broadcasts to the right and down? So are these blocks necessarily the same dimension as this block? Actually, once you have cyclicity, they're not quite. If you have a block layout, then they will be the same. So if you have a block layout where every processor owns a contiguous portion, then they have to be of equal size. We just have this one notion of blocks. But when we go to a block cyclic layout, let me scroll up a little bit. We are broadcasting something like this, where processor 8 owned this little block, this little block, this little block, and this little block. So the number of blocks he actually needs to broadcast overall is greater. So I guess you were also thinking about this block as a agglomerated task or a unit, while I mean overall what is a processor in this row sense, or in this column. And probably that's a more precise way of saying it. It's essentially if you have a processor that is involved in this panel factorization, then the amount of data they have to send horizontally in general might be bigger than this initial broadcast. And it will scale with respect to n divided by the square root of p. And if you notice then as you proceed with further broadcasts and further panels, you can kind of think of over time having all of these blocks broadcasted. So each block here will be broadcast once. In a sense, after we compute a block with L or a block with U, we broadcast it and then move on. So if all of the broadcasts are rooted at square root p processors at any given point in time, the overall volume of data they're broadcasting is n squared. So they will broadcast, and essentially your cost will be n squared over square root p. Okay, so that's jumping a couple of steps in terms of the analysis, but that's an intuition for where things come from. Okay, so for the 2D case, we have again essentially a load balanced block term, and then a block term associated with computing the diagonal blocks, which is also the same as the block term associated with factorizing the panels. Actually, no, there's also an n squared b term one can add here, which both of those become a problem. N squared over root p b term, when b becomes greater than n over root p. So if you have a very large block size, effectively such that the data is not distributed, you have some overheads. This is the one that grows fastest. So actually, yeah, this bound is because of that value and type. So the overall execution time is then given by something, this block plus scale, plus basically the broadcast we have to do. And the broadcasts correspond to the diagonal block broadcasts, which are of size b squared, of which we have to do a pair and go to square root p processors for each of the n over p diagonal blocks, as well as the panel broadcasts, which are distributed over square root p processors. The panels are. So each subpanel is effectively of this size. And it may not be contiguous in the overall matrix where each processor is broadcasting, but this term is a little bit bigger. So again, the analysis boils down to seeing what the collective communication here behaves like, and what we end up with is a cost where the bandwidth is proportional to n squared over square root p, which is the intuition that we saw that effectively we are broadcasting n squared data and panel updates overall. And the amount of concurrency in those broadcasts in the sense of different routes is never greater than square root p. So the amount of the bandwidth cost is n squared over square root p, while the latency cost is square root p. And the relationships between this denominator and this numerator are in fact can be shown to be formal. So if you multiply these two terms, you will get at least n squared. So there is kind of this trade-off in block size between these two. Does this cost remind you of any other algorithm we've already seen?
The conventional matrix multiplication.
Yes, for the 2D matrix multiplication algorithm, this is the exact cost. In fact, for the SUMA algorithm in particular, this is the exact cost you get asymptotically. So there you also have square root p stages where you broadcast a block row and a block column, which look almost exactly the same. They're an outer product like updates to the matrix. So you get in fact kind of the same broadcast structure and the same amount of computation overall. There's, of course, constant factors that are different for all of these that are involved, that are thrown under the rug here. But overall, the algorithms are very closely related. They basically multiply tall and skinny panels by short and fat panels to perform block outer products. However, life is not always as easy for LU as it is for matrix multiplication. Is there a simple reason to tell that it cannot be? So what is our kind of most fundamental bound on the speed up of an algorithm? The serial work. Well, but what is even better with respect to that? So for a serial algorithm, we can find two parameters: the amount of overall work it has to do, but also the longest sequence of dependent stuff, right? So that was called depth, or critical path was something a little different. But this is called the depth of your kind of DAG, of your computation. So with respect to the sequential work and the depth, what is a lower bound, an upper bound in the speed up? Or an arbitrary number of processors. So this depth D is that sequence of execution that you cannot parallelize. So what is a lower bound than your execution time?
Well, D is n over B, right? Because
Well, let's just speak abstractly of any algorithm. So we have a sequential amount of work we usually call Q1, and we have a depth D. So what is a lower bound than our parallel execution time? Can we derive one with respect to the depth D? Yeah, gamma times D. So there's D operations that will have to happen in sequence that we cannot parallelize. So the execution time will be at least the time it takes to execute those D operations, which is gamma times D. And what is our sequential execution time? If the work is Q1? Gamma Q1. Okay. So what is the maximum speed up that we can get? It's the maximum improvement that we can get using any number of processors in execution time. Yeah, Q1 over D. Yeah. So the work over the depth. So we can always divide work by depth to get an upper bound on speed up. This is also an upper bound in a number of processors we can strong scale to efficiently. That's the same thing as a speed up for a fixed problem. And so what is the longest chain of operations you see in LU. Yeah, the diagonal. So n. So what is the maximum speed up we can get for LU? The work is n cubed, right?
Cube over n
N squared. So yeah, the biggest amount of speed up we can get is n squared. We saw algorithms for matrix multiplication that could get a speed up of basically n cubed log n, assuming very fast communication. Matrix multiplication is more concurrent, substantially so, than LU factorization. So because of this, essentially, if you want to go to a 3D algorithm for LU, you will actually have to incur a higher latency cost. And you will not, in general, be able to get as good strong scaling as you can for matrix multiplication. And that can be shown formally. For instance, by this work over depth argument. So if you actually want to have an algorithm that takes less than n parallel steps for solving a linear system, you better not do LU. So now let's look at the scalability for the 2D case. So this is much along the lines of what we were just discussing. So what we saw for matrix multiplication is that Cannon's algorithm, which is very similar to SUMA, could achieve essentially unconditional weak scaling. So we have an algorithm that is very, very, basically the same cost as SUMA, and SUMA is very, very slightly slower than Cannon's algorithm, in particular by this logarithmic factor on latency. So all that Cannon's algorithm does with respect to SUMA, that is an improvement, is move from broadcast to shifts. And the only difference in our model between the cost of a shift of a given amount of data to a near neighbor process and of a broadcast is not in the bandwidth cost, but just in a logarithmic latency factor. And that's exactly this guy. Basically, this LU algorithm will get as good weak scaling as SUMA does, which is nearly ideal. So it's exponential in the initial problem size. So basically, if you want to get the scaling results for 2D LU, look at what we got for SUMA. On the other hand, essentially what we just discussed, the speed up is at most work over depth and at most n squared, so we cannot do as well with strong scaling as we were able to do with matrix multiplication. With matrix multiplication, the strongest result we got were from essentially memory tunable algorithms that used a variable amount of memory, and those could go effectively without using more memory than available to a speed up of n cubed over log n, while here the 2D algorithm is the best weak scaling speed up we can get, or strong scaling speed up we can get, and that's something like n squared over log n gamma over alpha. So it's a factor of n less. Okay. I guess before we do that, I'd like to actually give you guys a chance to discuss what is going to be the overhead of partial pivoting for the algorithms we've introduced, and how might you go about resolving that. So please talk to your neighbor for 5 minutes, and then we'll chat about that.
Layout of the processor. Yeah, I'd be able to carry processor.
Right.
It's also because like it's not just that every process needs to sort of know what the other is like their best what like so they need to like do like sort of
So as some hints, there is at least a few different things to talk about in terms of overheads. Actually computing which pivot row to pivot, figuring out how to pivot the trailing matrix rows and moving those, whether those two can be separated and which one is more of an overhead are both questions you can ask, as well as in which layout. And then you can also ask, okay, how do you go about trying to change things? So either a different pivoting strategy or maybe an algorithm altogether, or how can you just make partial pivoting work better? And I guess before, I should also remind everybody, so partial pivoting works, again, by finding the largest leading element in our column and moving that row to be the leading row of the matrix, and then proceeding with value factorization for every one of the columns in the matrix. Okay.
Like say this guy has the max, right? Yeah, so if we do a reduction with that max into the root into this guy, we'll change max, right? So we're doing a so you could maybe go with a tag and like tag the data, the double whatever with its processor, and then so and the root will like know who to swap with.
I think that's so. Once it knows that which row it need to be swapped with, then we can figure it out.
So on the first reduction, just the data just knows.
So I guess that process is what the
Yes.
find the whole
Double. It doesn't know.
What about moving the
Who had that shit
very
style?
style?
You could accelerate it. You could
Yeah.
start everybody.
Yeah.
Yeah, data is swapped later, so it's sort of like
It's just like logically.
I didn't get you.
well, yeah, that's what I want.
The pattern change communication pattern. I can be flexible.
But you might not want to do just a reduction. You could sort of like have these guys talk and these guys talk, and then like you can have so it's always like two kind of talking to each other. So like
First of all, we don't need a reduction step.
no, you want these two groups of two. Yeah. Just store the max here, and then it's this process and this process and talk.
This communication was very bad almost these
Latency.
guys.
Oh, if it's a slow node, then well, I mean, okay, talking about this way.
Yeah,
I mean, yeah.
Yeah, so what are some overheads of pivoting? I guess? In the first place, kind of, what kind of costs might change with respect to what we just saw, or what might get worse when we have to start doing partial pivoting?
Depends on the data layout.
Yes. So in particular, what data layout might be quite good for pivoting?
The one column.
One you count. In the sense that we don't need to send a message to compute the pivot. But what about the concurrency in computing? So that part is still kind of potentially a problem. Although we had this problem to start with, and the 1D layout is not very concurrent in the first place because the single processor is computing a whole panel. So now it's also responsible for doing all the pivoting, which may be okay, especially if we have not too many processors. So communication might not matter that much, but we don't want to have to synchronize for every single column of the matrix.
We're
Okay.
not going to actually move rows, right?
Sorry?
We're not going to actually move them.
Well, You don't have to, although you have to suffer, I think, either way. Essentially, when we have to move the rows, we can do so just for this element, and then do the factorization, or we can move this entire row. It depends on what we want to get and what we're okay with. And we can also consider permuting at a different time. So you're essentially suggesting that we don't touch the rest of this row, and we really just send information about the element here, and in fact, we just we treat from now on this row as the second row, as the first row of the matrix, and this is some arbitrary row. If we do that, we do have to keep track of locally which rows are kind of still active and which ones aren't, which does make your life a bit worse. So in particular, if you want to update them, you have to either update a block that includes this row. You have to either extract the row and make sure you don't overwrite it, or you have to deal with it somehow and only do partial updates. So I think this is played, and this is a pretty advanced trick, but it doesn't actually resolve some of the issues. In particular, if you have some reordering, when you have to do the update of those rows later, you need to figure out which are the right update rows. So you've switched your problem from essentially permuting the trailing matrix to permuting your updates, in a sense. But yes, that is something you can do. Okay. But yeah, what other overheads and what other strategies? That's a very good one. So essentially, avoiding, especially for this trailing matrix part of moving this row until you have to, is a good idea, and does appear in different algorithms. So I guess the basic overhead of pivoting we kind of discussed already, and that's the fact that if you have a 2D block layout, which is by analysis what we want in terms of communication cost, then for every one of the matrix columns, we have to do a reduction to compute what is the maximum element and what row we actually want to pivot. So the number of collectives we have to do is proportional to the number of columns in the matrix, which is n, which is a lot bigger than our square root p latency cost that we currently have now. So it makes us very sad. It's basically we have to send a message for every column instead of every block, or something proportional to the number of processes. So what would you potentially do to avoid it? Would you try a different pivoting strategy? How would that look like? Or would you try a different algorithm altogether for solving linear systems?
You just max elements in each block.
Yeah, so you can, one strategy you can use is to compute the maximum element in your current block. That's scary, especially if you're maybe at the end of a block locally. But yes, but as soon as you propose a strategy like that, we need to ask, okay, is it still stable? So is it still as robust as partial pivoting in terms of getting us the right answer? And so, in fact, there is a few different strategies for pivoting that have been discussed to replace partial pivoting, some of which are fairly robust, but they are more non-trivial than just looking locally or doing something that's totally parallel. So that's actually an area that I would say is a factor of research. What if you didn't want to do pivoting altogether of any type, and you just hated the whole concept of changing rows because it's such an unstructured communication pattern? What other algorithm could you use to solve linear systems? QR. Yeah. So with a QR factorization, you get an orthogonal matrix and a triangular matrix instead of a lower triangular and upper triangular. You can always compute QR stably if you only ever do orthogonal transformations, so you don't need to pivot while computing the R matrix. And you can solve your linear system by doing basically a forward substitution or backward, whichever one, followed by orthogonal transpose times the vector. So inverting an orthogonal matrix is also easy, and inverting a triangular matrix and multiplying by a vector is a triangular system solved. So yeah, actually, the reason people don't use QR is because it involves somewhat more flops than LU does, by a factor of about 2. In fact, a lot of people think now it might be a good idea to always just use QR and not really worry very much about LU, because when you look at something like pivoting and the communication costs associated with it, it probably hurts your efficiency by more than a factor of 2 unless you're running some function. Okay, but we'll continue with that in a little bit more detail on Thursday.